Okay. Good afternoon, everybody, and welcome to the last talk we have in the PAC-Bayes seminar series. As always, here are the links for you to share. As always, please use the Q&A function in Zoom if you have talks throughout, and we will interrupt Badr, and we'll have time at the end for some questions. Yep, as I say, so we've seen a lot of different sort of sides to PAC-Bayes so far, and we're finishing up today with Badr. Badr is at the CNRS and Sorbonne, and having had the pleasure of working with him, I'm really excited to see what he has to say about the sort of interface between PAC-Bayes and variational inference. So over to you, Badr.
Yeah, okay. Okay, so thanks a lot again for the introduction and for the invitation. So don't hesitate. So I mean, like these slides have been designed for this seminar series. So if anything is unclear or so, just like don't hesitate. I mean, I don't know how you guys want to deal with this, but don't hesitate to like ask questions during my talk. That's very nice. So today's talk is about PAC-Bayes and variational inference. So many of the ideas that are developed here will rely a lot on the previous chapters in the seminar series. So in particular on chapter 1 and 3. So the one on generalized base and the one on PAC-Bayes. And really the goal of this talk is to see and understand how PAC-Bayes tools can be used to analyze the behavior of generalized posteriors in general, and in particular in variational of posterior approximation that are defined by variational inference. So this has been very shortly mentioned by Pierre in his introductory talk on the PAC-Bayes, so the first talk of the chapter, and I will try to delve a bit more in details in this talk. So the first part of the talk will just like be a short introduction and a reminder, maybe not always reminders, but mainly reminders on some tools that have been introduced in chapter 1 and 3, right? The second part is a proper definition of what is variational inference, how it has been originally defined, how it can be understood. So kind of two different perspectives on the same concept. The third one is I will try to I will try to make clear how PAC-Bayes can be used to analyze Gibbs posteriors and how this analysis can be extended to variational posteriors. And finally, a few points to be discussed and a few generalizations. So first, to start, so a very general definition of generalized base. Okay, so generalized base is mainly the main topic of this seminar series. So I don't think there is a need to spend too much time here. But typically, we are statisticians, so we have a data set, okay, which is given. If we are proper statisticians and we want to define a statistical model, and as Bayesians or as pseudo-Bayesians prior distribution, then we can define the Bayesian posterior, which I think we are all familiar with. Or if you're more in a learning setting and you do not necessarily want to deal with any statistical model, you can just define the loss, okay, and consider what is called the Gibbs posterior, and that has been introduced like many times before my talk. So simply, the Gibbs posterior is a generalization of the Bayesian posterior, where the statistical model is replaced by a loss with an additional parameter, which is the temperature parameter here, lambda n. So I wrote the index n just to highlight the fact that the temperature parameter can or not depend on the sample size. So here n is the sample size. And typically, if you take the temperature parameter lambda equal to 1 and so if you have a statistical model and you consider the loss to be minus the log density, okay, then you exactly recover the base posterior. And so I defined here the Gibbs posterior because it will be the main focus of today's talk. So we will discuss what will happen when we have a proper statistical model and we consider the Bayes posterior, the regular Bayes posterior instead of a general Gibbs posterior. But from now on, we'll mostly work with the Gibbs posterior in hand, right? So now this is a question that has been explicitly raised by David, so David Fraser in his, I think it was the second talk of the series. And his question was, why should we consider the Gibbs posterior? Why is it relevant? So there are many, many, many answers to this question. All of them are really relevant, but there is a precise axis he rated his answer to, which is what he called the reasonableness in terms of large sample behavior. So his idea was very simple. He says that there should be an optimal parameter theta star, and he says, okay, the Gibbs posterior is a reasonable posterior belief if the posterior distribution, so the Gibbs posterior, concentrates most of its mass as the sample size grows toward this optimal parameter, right? So we have a loss. So the optimal parameter here is the one that minimizes the loss, typically. Okay, so I will define it properly, but this is basically one of the notions he considers to measure the notion of reasonableness, okay? And this is called posterior concentration. So once again, there are many other aspects you would like to consider to evaluate the quality of a posterior, but this is the one we'll focus on today, posterior concentration, right? And typically, to use the exact words of David, he presented something he called the old school theory for that. So typically, the historical tools that have been used to derive explicit concentration of the posterior with rates of convergence. So if you did not attend his talk, I mean, I really invite you to do so because I mean to watch it on YouTube. I think it's on YouTube because it was very interesting and there are a lot of insightful ideas there. And he also mentioned what he called the new school theory, which is typically based on PAC-Bayes. So I don't think there is one approach that is better than the other, but there is a very convenient thing with the PAC-Bayes approach, which is that it can be very easily extendable to analyze approximations of posteriors. So this is the one I will try to develop a bit in this talk, both once again for analyzing the posterior itself, but its approximation, right? So to define things properly, so consider that our data set is a collection of independent random variables that have a common distribution, a data generating process, say P star, okay? So P star here is unknown. We just assume it exists. And from this data generating process, we define two objects, the population loss, okay, which is the expectation of the loss, and the empirical loss, which is the empirical average of the losses evaluated at each data point, right? So this is very, very classical definition, population loss, empirical loss. And of course, our goal, our hope here is that the posterior concentrates most of its mass toward the population loss minimizer. So here, the quantity of interest, in some sense, is the population loss minimizer, theta star, and we hope that the posterior concentrates to this specific point, which means the following. So this is exactly the definition that David used in his talk. I mean, typically there are several variants of this definition. Either is the convergence in expectation with high probability also. I think that this variant in expectation is great. And it's something that is very natural. What does that mean? It means that as the sample size grows and goes to infinity, when you consider a neighborhood of the parameter, the target parameter theta star, then the mass assigned by the posterior outside of this neighborhood should go to zero. So in some sense, the whole posterior mass of the posterior should be located near the parameter theta star, right? And so there are two components here, two additional components. The one is the notion of how you measure the neighborhood, okay? So you need to define a metric between parameters to define the neighborhood. So this has to be discussed later. And the second point is the radius of the neighborhood, okay? And this is very simple. The radius of the neighborhood that you're considering will characterize the rate of convergence, okay? So we have concentration at some rate if, so you have this definition that is satisfied with the rate of convergence being the radius of the neighborhoods, right? And typically, the result that has been formulated by David Fraser, so in his talk is the following. So you have concentration of the Gibbs posterior provided two general set of conditions. So the first one is a prior mass condition, which is quite natural. In some sense, it says that the prior is not too bad in the sense that if the prior distribution assign all its mass very, very, very far away from theta star, then there is very little hope that we'll get concentration. If at the opposite, the prior distribution assign a non-negligible mass around theta star, then it means that the prior is not that bad and there is like high hope of achieving concentration. And the higher mass near theta star, of course, the quicker the convergence. So this is typically the first condition, and the second set of condition is something that he summarized in the following terms, like a well-behaved loss. So once again, if you did not attend his talk, I really invite you to do so, because he formulated actually several different definitions of what he calls a well-behaved loss. So I wasn't really aware of the equivalence of all these conditions. We will not really enumerate all of them here. And typically, you can assume one thing, which is that if the loss is bounded, basically, then your loss will be well-behaved, okay? So this is a really simplified assumption, but this is the one that we'll use today, okay? We'll say, okay, the well-behavedness will be okay if our loss is bounded. Once again, this is not what the core assumption, and there are many different ways of satisfying these well-behavedness conditions, but just to think of it very simply, in very simple terms, just think that your loss is bounded, okay? And of course, his result is very like, this is a very general result in the sense that I did not say anything about the choice of the metric. I didn't say anything in the sense of, in terms of the temperature parameters. We will see how the rate of convergence depends on the temperature parameter and what choice of the exercise should be we should have so that we have concentration, okay? So the next slide is just a very, how to say, kind of a teaser of what we'll do today, of at least some part of what we'll do today, how we can establish concentration of the posterior using PAC-Bayes tools. So what I just wrote here is exactly the same thing at the definition of concentration. It's exactly the same thing. What we target, what we want to derive is the concentration to 0 of this quantity, okay? So the expectation with respect to the data of the posterior mass of complements of neighborhoods around the true parameter. And the question is, how can we use PAC-Bayes tools to show this? The proof is in fact very simple. There are typically two arguments. The first argument is Markov's inequality, which I think is very basic, and all of you are very familiar with that. So typically, the idea is to say, okay, I want to control a posterior mass. The posterior mass, typically, it's a tail, okay, probability tail. And so Markov says that a probability tail is always upper bounded by the expectation, the ratio of the expectation of the random variable that you consider, divided by the threshold, right? So here, the random variable that we consider is the distance between theta and theta star, right? So I take here on the numerator the distance between theta and theta star. So here, theta is a random variable, okay? It follows the posterior distribution. And mn multiplied by epsilon n is the threshold. So in some sense, it is in the denominator, right? So here, just notice that I use two different colors. One color, the red color refers to expectations, randomness with respect to the data generating process, whereas, so it's like the data are random here, and the expectation in green refers to randomness in the parameters. So the parameter is random here, okay. And now, so to achieve the consistency to zero of the quantity on the left-hand side of the inequality, it is sufficient to establish the following result, which means that the numerator is upper bounded by epsilon n. Why so? Because if the numerator is upper bounded by epsilon n, then the ratio will be upper bounded by epsilon n divided by mn epsilon n. So the two epsilon n cancel out, and we just have, in the end, 1 over mn, and mn goes to 0 by definition as the sample size goes to infinity, so the quantity of the right-hand side will go to infinity. So in fact, if you want to prove concentration of your posterior, it is just enough to establish this kind of highlighted inequality. And this is where PAC-Bayes enters the room. In fact, PAC-Bayes gives us tools to do so. So here, so this is the second ingredient. So this is a PAC-Bayes bound. So I guess that you don't have this PAC-Bayes bound in mind, sorry, of course. In fact, it has been given by Pierre, like in his introductory talk a few weeks ago. So of course, it may be a bit abstract as mentioned like that, but typically we will prove it formally in a few slides. But just keep in mind that as soon as you have a PAC-Bayes bound on this kind, typically what it brings you is a rate of convergence. Because if you choose the excess risk metric as being the population loss minus the minimal value of the population loss, okay, which is typically the excess risk metric, then actually you have this kind of inequality. This inequality is exactly this inequality here, with epsilon n being with epsilon n being the sum of the terms in lambda n and 1 over lambda n. So in the end, with this typical sketch of proof, you end up with a rate of concentration, which is over the temperature parameter plus 1 over temperature parameter multiplied by the sample size. Okay, so how you obtain these two terms is like, so once again, I will explain that in more details later. But I just give you that, and so I give you that for granted. But typically, just to say that typically achieving deriving concentration rates is in fact very simple as soon as you know a few PAC-Bayes bounds. Okay, the only difficulty here is to derive this exact PAC-Bayes bound. Okay, so this is really a sketch of the proof that has been that I will like detail later. And if I had to say a few words, so this is exactly the result I just mentioned later. So earlier, sorry. So the Gibbs posterior, in fact, concentrates. So of course, provided your loss is bounded and the prior mass condition is satisfied, with respect to the excess risk at rate lambda n plus 1 over lambda n multiplied by n. So this is the exact, at least an upper bound, but the rate of convergence that you're guaranteed to have on your Gibbs posterior. So two very short remarks. The first one is that we could question the relevance of the different assumptions. So the prior mass assumption is very natural. The boundedness assumption of the loss could be questioned, but in a learning framework, it's a pretty basic one. So we say that we are okay for the moment. We will discuss this assumption later. And the second one is that, so if you attended like I think it is the third talk of the seminar series, the talk of Ryan Martin, he gave a very long talk on the choice of the temperature parameter. So once again, there are very different ways of evaluating the quality of a temperature parameter. This result gives some perspective, some PAC-Bayes perspective or some concentration perspective on the choice of the temperature parameter that you should adopt. So basically, it says that, okay, if you want your concentration to be quick, then you should choose a temperature parameter lambda, which in some way optimizes this rate of convergence. And you can see that the choice of lambda that balances the two terms in the rate of convergence is a lambda equal to, or at least proportional to n to the, so 1 over the square root of n, which typically leads to a concentration rate in 1 over the square root of n. Okay, so this is typically what we can have. And a last word, which is that all these rates that I mentioned are up to a logarithmic term. Okay, so it's not exactly, in the end, you will not get 1 over the square root of n. You get log n divided by the square root of n, but I on purpose, I just like get rid of the log n terms, logarithmic terms in this talk. Okay. So this is what we can say for the moment, but this is not really the topic, the main theme, today's theme, which is like typically variational approximations. And so what is the problem here? It's that actually the Gibbs posterior is rarely computable in practice. Like in many complex models, you don't have a closed form formula for the posterior. And so in this kind of situations, what you can do is to approximate, so this is a possibility among others, to approximate the Gibbs posterior using typically variational inference, which is today's topic. And the question we'll try to answer is, okay, when you consider the Gibbs posterior, you know that the Gibbs posterior concentrates at some nice rates. You cannot compute it, but you can replace it by an approximation. But does the approximation retain the exact properties, concentration properties of the posterior it approximates, right? This is typically the question we'll try to answer and to understand properly, right? So now I will very shortly define what variational inference is. So the idea is very simple. In fact, variational inference is an approximate Bayes technique. So the idea is to approximate a generalized Bayes posterior, so here the Gibbs posterior. And the problem, if you want to identify the problem, quite often the problem is that there is a normalizing constant that you cannot compute. So here Z is the normalizing constant in the definition of the Gibbs posterior. And this normalizing constant is not always tractable. The idea of variational inference is very simple. It says, okay, I cannot compute explicitly my posterior. So what I will do is that I will consider an alternative set of tractable distributions, and I will choose in this variational set of tractable distribution the one that resembles the most the target, the Gibbs posterior. Okay. And how do I define this closeness? I use what we call the reverse scale, which means that it's the scale divergence between the approximation and the target. The target is on the right-hand side of the scale. Okay, so it's something that's very simple. Actually, you consider a variational set of approximations, you consider your target, and you project your target onto this variational set, projection being defined with respect to the reverse scale divergence. Okay, so there exist many different families of approximations. The first one that comes to mind is a family of Gaussian distributions. So you say, okay, my distribution maybe looks like a Gaussian, but is not a Gaussian. So I just decide to approximate it by a Gaussian. This is a possibility. Another possibility is to say, okay, I choose a mean field family. What does that mean? It means that if you can write your parameter space as a product of different subparameter spaces, then you say, okay, I will put like independence on the different components of my parameter. So typically, if you have a mixture model, you can say, okay, okay, imagine that you have two components and y weight parameter. Then you can say, okay, I will define my approximation as setting three distributions, one on the weight, one on the first component, one on the second component, without any restriction, but the fact that all the distributions are independent. This is another possibility, right? So the idea is very simple. Once again, variational inference is an approximation scheme technique, which aims at just approximating the posterior by the closest distribution in a given set. Nothing more complicated. And there is a question here that comes to mind, which is why should we choose the exclusive KL? Because there are many ways to define the closeness between distributions, how close they are or not. And even if you consider the KL divergence, there is no reason to choose in particular the KL, the exclusive KL, like the reverse KL, rather than the other way around, right? So the question is, why should we consider the exclusive KL when defining closeness? And the answer is very simple. In fact, the reason is that, okay, when you're saying I'm doing variational inference, you want to replace a distribution that is intractable by one that is tractable, but to do so, you define an optimization problem. You're minimizing a KL between Q, so the distribution over which you minimize, and the posterior. But the problem is that this problem, this optimization problem in itself still contains the problem, which is the normalizing constant, okay? Okay, in the end, if you are able to solve this problem and to minimize the objective, the KL objective, then in the end, you will get something that is tractable, a distribution which is tractable. But to choose this tractable distribution, you need to solve a problem that contains an intractable term. And really, the advantage here is that if you just develop the KL distribution using the additivity of the log and the definition of the Gibbs posterior, in fact, you end up with the sum of three terms, and one of the three terms contains the normalizing constant z, and is the only term that contains the normalizing constant. What does that mean? It means that if you minimize this with respect to q, then it is equivalent to minimizing this plus this with respect to q. And why the sum of these two last terms? Because the first term here does not contain the variable q at all. So in fact, the optimization problem can be split in the optimization, the minimization of two terms, one that contains the variable over which you minimize, so the q, and another that contains the normalizing constant z, which was the problem, but which does not contain the optimization problem anymore. So in some sense, it is equivalent to minimize your KL objective or to minimize the sum of these two terms, right? So here, what I did, so I said that minimizing this is equivalent to minimizing that. So I can remove the log z because it does not contain the constant q, parameter q, the distribution q over which we minimize. And here I just divided by lambda n over n. So as you can see, I divide this by lambda n over n. And here, if you divide by lambda n, you remove the lambda n. And if you divide by n, then you exactly get the empirical loss, right? So in fact, variational inference is equivalent to two things. You have the original definition, which is doing approximate Bayes, so approximating the posterior. But there is another definition of variational inference, which is solving an optimization problem, a regularized optimization problem over the space of distribution, okay? So if you attended Pierre's talk, so Pierre Alquier's talk, like a few weeks ago, then you can notice that this is actually the way he defined variational inference, which is very convenient when you're doing PAC-Bayes. I will just explain why in the next slide, but which is not the original definition of PAC-Bayes, and is not even like the approximate Bayes approach perspective of PAC-Bayes, okay? And so you have two different perspectives that you can have on variational inference. The first one is an approximate Bayes perspective. So you try to find the distribution, the tractable distribution that is the closest to the target. And you have the second one that says, okay, you can directly just target an optimization, design an optimization objective that will minimize over the variational set. The only thing is that the minimization here is not on the whole space of distributions, but over the variational set that you define. So constraint, then optimize, right? And if you attended the first chapter of the seminar series, then you really recognize this optimization objective. And in particular, I think that the first slide of David's talk defines the Gibbs posterior exactly like that. So in fact, this is this definition of the variational approximation is exactly the one I wrote in the previous slide. And the second definition here is an alternative definition of the Gibbs posterior. So, okay, I give it like, I just like write it down here from nowhere. But this is something that has been like mentioned a lot of times in the, I mean, I think in the introductory slides of Jeremiah's, then by David and so on. Just like many slides. This is an alternative definition of the Gibbs posterior. And what just am I highlighting here, which is that the Gibbs posterior and its variational approximation, they in fact minimize the exact same objective. The only difference is that the Gibbs posterior minimizes the objective over the whole space of probability distributions, while its approximation minimizes this objective, but only over a smaller subset of distributions, right? Over the variational set. But still, in some sense, so you can see the Gibbs as an object that is principled and the variational approximation as a copy of it, okay? But you can also see the two objects as almost the same objects in the sense that they solve the same optimization problem over kind of differences, okay? And why is it very interesting to adopt this perspective on VI? It is that actually, well, just to prove, actually the question is, how do I prove concentration and do I derive rates of concentration for the Gibbs posterior? Actually, I exactly use this definition of the posterior. In fact, there is a PAC-Bayes bound that has been given by Olivier Catoni in 2003 and has been given by Pierre in his previous talk, which is exactly the following. What does that say? It says that in expectation, the population loss, okay, is upper bounded by the empirical loss, so in expectation, once again, plus the KL, the ratio of the KL over lambda n, plus another additional term, right? So this PAC-Bayes bound holds uniformly over all posterior distributions, okay? So it holds uniformly over all posterior distributions. So in particular, it holds for the Gibbs posterior, right? And it turns out that actually, if you just like take a look at the definition of the Gibbs posterior, actually the Gibbs posterior is the distribution that minimizes the right-hand side, right? And this is very convenient because this is, in fact, this is the way we derive rates of convergence. We say, okay, we have a PAC-Bayes bound, we will do something with this PAC-Bayes bound, but in particular, we will use the fact that this PAC-Bayes bound is minimized by the Gibbs posterior. And this is how we derive a rate of convergence for the Gibbs posterior. But we can have exactly the same remark for the approximation. In fact, the variational approximation also minimizes this PAC-Bayes bound. It's just that the minimization is not performed over the same set of distributions, but still the posterior distribution minimizes this PAC-Bayes bound. And so this is the only requirement that we have to derive rates of convergence to express our posterior or our approximation here as the minimizer of some bound that we have. We have Cantonese bound. We know that the approximation is a minimizer of Cantonese bound. This is enough to derive rates of convergence, right? So this is exactly what we will do in the slides, in the following slides, right? Great. Are there any questions or do I go on?
Keep going, I think.
Great. Okay, so now I will, great, thanks. So now I will, so this part will be a bit technical, not very complicated, I think, but a bit technical. So just we'll have like derive the proofs properly and so on. So just a few reminder. So what I mean when I'm saying that I want to derive a concentration rate, so for now we consider the excess risk metric, is to derive the following, okay? We want to show that the posterior mass of the complements of the neighborhood go to zero as the sample size goes to infinity, right? And the fact is that we showed, I mean, remind just like in the first slides of the talk, we show that it is in fact enough to have this kind of PAC-Bayes inequality. Okay? So why so? Because then Markov's inequality says this, and the term in the right-hand side here goes to 0. So the only thing we want to do here is to derive this kind of inequality, okay? And what we'll do to derive this kind of inequality is that we will exploit Cattonese inequality, Cattonese bound, to derive this inequality, okay? So let's do things like one after the other. Our goal, just a reminder, what we want to do. We want to derive this kind of inequality. We want to say that in expectation over the data set and in expectation over the parameter following the posterior, the Gibbs posterior. So for the moment, we are focusing on the Gibbs posterior, and then we'll see how we can extend the analysis to approximations. Then the population loss is bounded by the minimum of the population loss plus the rate of convergence. So for the moment, we don't know what the convergence rate is, but we will just like derive it explicitly. The first ingredient is to apply Cattonese inequality. So rewind what Cattonese inequality is. Cattonese bound says that in expectation over any Q, the expectation of the population loss is upper bounded by the expectation of the empirical loss plus the KL over lambda plus lambda over 8, okay? This was valid for any Q, so in particular for Q being the posterior distribution, right? So I replace Q by the posterior distribution here, here, and here, okay? Then I notice that by definition, or by property of the Gibbs posterior, then it is the minimizer of these two terms here in the expectation. So I just replace the sum of these two terms by this infimum, okay? Once again, this is a characterization of the Gibbs posterior. The Gibbs posterior minimizes this quantity, okay? Then from the second line to the third one, what I'm doing is that I'm swapping the infimum and the expectation. So I cannot do it for free, it's an upper bound, but that's okay, right? And then what I have is that here I have the expectation inside the infimum, and so I can swap the two expectations, and of course the expectation of the empirical loss is just the population loss. Here the expectation doesn't change anything, so I end up with this bound, okay? So what did I do in some sense? I started from a uniform empirical bound. So why do I say uniform? Because it was valid for any Q. Why is it empirical bound? Because the population loss was bounded by an empirical loss. And I end up with an oracle inequality in the sense that I have the population loss in the left-hand side and in the right-hand side, okay? This is convenient because in the end, what I want to compare my expectation here is a population loss. So it is important not to have an empirical loss here, but to have a population loss. So this is really the first part of the proof, right? Okay. From now, what can I do? And actually, the key point is to say, actually, it's not really relevant to consider the infimum over all distributions. Because in the end, what we target is just theta star, right? So in fact, I cannot consider a delta mass here because the KL between a delta mass and pi will be infinite, okay? But still, I will try to consider distributions that are sufficiently concentrated around theta star. And the kind of distribution I will choose are the distributions that are defined as exactly the prior, but truncated on a small neighborhood around theta star, okay? So it's what I'm saying. I'm choosing a radius around theta star, and I'm saying, okay, if you're inside this neighborhood, then my distribution PR is just pi. But if I'm outside of this small neighborhood, then I put my posterior distribution here as being equal to 0. Okay, so I have to renormalize then, of course. But this is something that is very, very natural. I mean, when you consider a posterior, for instance, the posterior, if you have a very large sample size, then it is like very peaked around theta star. this is approximately the same idea, but even stronger, like it's a truncation, okay? If you're near theta star, then you consider pi. If you're not near theta star, then you consider 0. Okay? The idea is really to consider only, so you cannot consider theta star precisely, but it's almost equal to theta star. It's equal to theta star up to an R, okay? And what we're saying is that instead of considering the infimum over all distributions, just consider the infimum over this kind of distributions, okay? So these kind of distributions are indexed by the radius, so you just minimize over the radius, but this is basically the idea. So if you attended like the talks of Pierre, he exactly mentioned that very shortly in a slide to motivate how we can derive such rates of convergence, but this is exactly the same idea. Maybe the notations are slightly different because it was in different contexts, but this is exactly the same idea. Just consider truncated priors near the theta star, okay? Now this is done, okay? So this is exactly, so this is just a reminder of what I did previously. The question is how do you use this kind of truncated distributions? In fact, there is a property, which is that the losses, actually, how do I define the neighborhood? I define the neighborhood as the parameter theta such that the loss is smaller than the infimum loss plus R. Okay, so here, any theta here that I consider is upper bounded by the loss of theta star plus R, right? Sorry, this plus this. So the expectation can be handled very easily. And the second part that is remaining is the scale. And in fact, you can compute explicitly the scale very easily. You have an explicit form for PR. You know what P is equal to. So if you just develop by definition of the KL, then you exactly get minus log of PR. Okay. And then if you put the L of theta star outside of the infimum, you get L of theta star plus the infimum over all R of this plus lambda over 8. So this is just like, okay, maybe it's not very small in like during the talk, but this is very basic computations that you just have to follow to understand really what happens. This is quite important to understand that this is really what we're doing when you're deriving rates of concentration. And there is one last part, just to conclude, is just to say, okay, actually, we assume something, the prior mass, because you see that here, all the terms that are remaining here depend on the quantity, which is the mass of the prior. And what does the prior mass say? The prior mass says that the mass assigned by the prior to neighborhoods of theta star is not zero, like not negligible, not completely negligible. And this is exactly what I assumed here. So here, I assume a very specific form of the prior mass condition, which is satisfied mainly in parametric settings. So you could extend in this definition to non-parametric setting as well, very easily. But what you just need to keep in mind is that the prior mass of neighborhoods around theta star is not negligible. Okay, it's not zero or really almost zero. Okay, it can be small, but not negligible. And if under this assumption, it's very easy to upper bound minus this log by this. Okay. And then in the end, if you optimize with respect to R, you exactly got this bound. And so in the end, you have just like the sum of two terms here, they say it's of order lambda n. And the term here is not exactly lambda n, but lambda n, 1 over lambda n up to a log, okay? And so in the end, what we get is this rate of concentration up to a log, okay? This may be a bit long to like a lot of details to follow, but I think it's pretty important to understand that, or at least to follow that in the main lines, to understand how we can how we can prove things for variational approximations. Okay, even if all the points here are not completely clear to you, having just like a big picture of what happens is important to see how we can understand the behavioral approximations. It's exactly the same sketch of proof, okay? So now, if I'm interested in approximations rather than the exact Gibbs posteriors, I follow the exact same line, okay? I begin by applying Cattonese inequality, Cattonese bound, and I'm saying, okay, this is smaller than that. And it turns out that this is exactly minimized. I mean, sorry, this is exactly minimized by the variational approximation, but over Q. So the only difference with what was previously written is the fact that instead of minimizing here over the whole parameter space, the whole space of distribution, we just minimize over the variational set. But this is exactly the same thing as this bound. We have the exact same bound. We replace the posterior here by the variational approximation. We get exactly this bound, but by restricting ourselves over Q instead of the whole space of distributions, right? And here I could say, okay, no, so now I have the same same kind of proof, so I can just go on. But here is the problem. The problem is that previously I said, okay, instead of minimizing over the whole space, I just minimize over, the truncated priors. But this is not possible anymore. Why so? Because this family of prior distribution do not necessarily belong to this variational set in some sense. So here is the key difficulty. If you want to extend the previous proof to the case of variational approximations. And the question, which is, what should I do, is in fact very simple. In the end, what do I want to do? I want to have a bound like that. Actually, it's exactly what I did by choosing this kind of truncated sets and then using the prior mass condition. In the end, I ended up with that. Okay, the point is that here, as I cannot choose this family of truncated distributions, it's not obvious how I should derive this. And there is a very simple answer to that. How can I derive that? The answer is just assume it. So if you just decide to assume this, then you can extend your previous result from the Gibbs posteriors to the approximation. This is very simple, in fact. Just saying, okay, I was able to show something previously because I had the tools. Now I don't really have the tool. How can I get this result? I assume that. So you could say, okay, it's cheating. It is true in some sense. But the question is, okay, is it really cheating, right? So my requirement is this one. So as I told you, okay, it's an assumption. So it exactly means that I just have to assume that the first part here is upper bounded by that, and the second part here is the KL is upper bounded by 1 up to a log. Okay, so this is, I mean, if this is upper bounded by that, then you still have, it still satisfies the bound, and if the KL is upper bounded by 1, then you still have the 1 over lambda in n, that it's still okay. So the only thing I assume is that I have a sequence of distribution Qn, of variational distribution, that satisfy both the first condition and the second one. And these two conditions, jointly, or what I could call, I don't really know how we should call that, but I would say an extended prior mass condition. So maybe it's not obvious to you what is the relationship with the prior mass condition, but it will maybe become clear a bit later. Okay, just to say that the informal result is that under the extended prior mass condition, so the condition above, and if my loss is bounded, then my variational approximation concentrates at the exact same rate as the Gibbs posterior. Okay, so this is just what I want you to keep in mind. And now what we have to do is to discuss whether or not the extended prior mass condition is cheating or not. Okay. And the answer is not really, in fact, not really. In fact, there are many settings where the prior mass condition, so it's not yes or are we cheating, it's yes or to the question like, is it realistic? And in fact, I will just give you two examples where the extension of the prior mass condition is roughly equivalent to the prior mass condition. The first one is the setting where the variational set is the space of the whole distributions. I mean, this is exactly as saying, okay, I'm considering the Gibbs posterior, the exact Gibbs posterior itself, because if I optimize or approximate the Gibbs posterior using any distribution, of course, the closest distribution to the Gibbs posterior is the Gibbs posterior. So it's as if I was considering the Gibbs posterior. And actually, there exists a distribution satisfying both this, which is, well, the truncated prior distribution, okay? So if you use like a small radius and a truncated prior distribution, that you exactly satisfy, then this truncated distribution will exactly satisfy the extended prior mass condition. But now the question is what if I do not optimize over the whole set of distributions? What do I get? Actually, imagine that I choose my set of approximations as Gaussian distributions. Then I can tell you something, which is that as soon as the approximation is Gaussian and the loss is Lipschitz, then the extended prior mass condition is satisfied. And in fact, I can even tell you what choice of Gaussian I should choose. And to understand this, just keep in mind, what am I doing when I'm considering truncated Gaussians? What I'm saying is that I just want, in some sense, to consider distributions which are very close to theta star, okay? So I'm doing a truncation. If you're far from theta star, your mass is 0. If you're close to theta star, your mass is the one of my prior up to the renormalization. In fact, there is no possibility to consider this truncation because it does not belong to the variational set. A very simple way to do this is actually to consider a smooth approximation. So instead of considering the truncation, just consider a Gaussian, which is very close to this truncation, right? So by doing so, you will be able, in some sense, to control this KL divergence, like the KL between two Gaussians, like you would just get a logarithmic term in the sample size, which is like not negligible, but it belongs to up to the log terms. And the second thing is that if you want this to be satisfied, then like the Lipschitz kind of Lipschitz condition will be enough in some sense, okay? Once again, if you choose a truncated Gaussian, then you belong to the neighborhood. So this condition is naturally satisfied. If you cannot truncate hardly, then a structural assumption, such as like Lipschitzianity, will be enough, okay? So what you have to keep in mind is that, okay, if my variational set does not contain the kind of distribution I would like typically my variational set of distribution is Gaussian, then typically if there is some structure in the loss that is still here, so a Lipschitz lot typically consider a logistic regression, like it would work. And there just like a loss that is not anything, like not a very bad loss, then you still have some warranty, and actually your approximation retain the same properties as the initial posterior to approximate, right? So this was quite of a bit long like sequence on that, but just what I want you to keep in mind is that, in fact, the key point for establishing rates of concentration for Gibbs posteriors is PAC-Bayes theory, okay? And it turns out that you can do this because a Gibbs posterior is the minimizer of Cattonese PAC-Bayes bound. But it turns out that its variational approximation is also a minimizer of Cattonese PAC-Bayes bound, which is very convenient. So in some sense, extending the proof is not that simple, it's not that complicated, sorry, provided that you have some structure that is nice enough, okay? Within the proof, whenever you will choose like something that is a truncation or something like that, you can choose a smooth approximation of that, and it will be okay, right? So it depends as well on your set of approximation, but on the nature of the loss. Okay? Great. So now that we've done this, I will criticize a bit what I've just like talked about for a moment, okay? So my first criticism is the following. Imagine that I'm a statistician and I have a statistical model. So very shortly, we're running out of time. So very shortly, imagine that I'm a statistician. So I consider my loss to be minus log density. Then the excess risk metric here would be just the KL between the true parameter, p theta star and p theta. assume that my data generating process is p theta star. Then what I have is that I have concentration at rate lambda plus 1 over lambda n, provided the prime mass condition and the boundedness of the loss. What does that mean, having a loss that is bounded? Here, it means that my density is lower bounded, which is a very strange assumption, actually. So we see that the previous result does not really generalize easily to statistical modeling. And so there are three criticisms here, mainly. The boundedness assumption is really relevant in learning frameworks when you are in classification and you have the 0-1 loss or things like that, but not really in statistics. The second one is that actually here, to get concentration, you need to have this that goes to 0. And basically, if lambda n is fixed and does not go to 0, then, I mean, you don't have concentration. And typically, in the base posterior, you have like lambda is equal to 1. So it's strange. And the third criticism is that even if you tune your lambda n, then what you have is n, it's like the optimal rate of concentration that you can get is 1 over the square root of n. Whereas in KL divergence, we should get something like 1 over n in statistics, which is a bit strange. So there are a few criticisms. And what is the problem with that? Is that typically, I just like reminded two results that exist in the literature. The first one is to say that, okay, the regular base posterior is known to concentrate at rate 1 over n in squared Hellinger distance, typically, for instance. And the second result is that, so provided additional test conditions. And the second result is that if you consider the temper posterior, so with lambda smaller than 1, then it is known that you have concentration at a rate slightly slower than 1 over n, but still something that is like better than 1 over the square root of n. And typically what I'm saying this is that because here, typically, if you consider the squared Hellinger distance, it is roughly equivalent to the KL in regular parametric models. And you see that we have a rate of concentration here, which is much faster than this one, and which is at the same time which relies on much lighter conditions. So these results that do not follow from PAC-based tools, just like make us, there is a need to rethink in some sense what we just did. So very shortly, just to say, in fact, if we just apply the Catonese bound to the log loss, then we will get this, okay? And you see that as if lambda does not go to 0, then we cannot conclude in some sense. We have a bound that is just vacuous, okay? This is, I mean, so this is the negative log likelihood ratio. Just apply Catonese bound to the log loss. We get this bound, which is actually irrelevant. So the problem with what we did is not that there is anything wrong. It's just that the bound we relied on is actually useless. So if we want to get something interesting for the base posterior and for the temper posterior, we need to rely on other bounds that are relevant. And typically, are there some other bounds that are relevant? The answer is yes for the temper posterior. If you consider lambda strictly smaller than 1, even constant, you can get rid of this additional term that is non-vacuous when lambda does not go to 0. This is at the price of a slightly larger factor here. But what we have is that the Gibbs posterior and its approximation are both minimized over this bound, and this bound is not vacuous. So we'll be able to derive quite easily concentration rates for both the temper posterior and the approximation of the temper posterior, okay? So here, BPY, so it's Bhattacharya, and Yang, who proved the bound and the rates of concentration for the exact temper posterior. And then, so YPB is like Bhattacharya, and Yang, but in the other way around. And the AR, it's like Pierre Alquier and James Ridgway that proved the extension to variational approximations, okay? So the key message here is just like, we can easily extend the result of the Gibbs to statistical models, okay, to model base posteriors. The only thing to do is to choose another PAC-based bound to start from, okay? And what can we do if we focus on the exact posterior? So for lambda equal to 1, actually nothing in some sense. So I'm not saying we cannot do anything. I'm just saying that to the best of my knowledge, there is no PAC-based bound which is minimized by the exact base posterior and which is not really non-vacuous. And so what does that mean? It means that, to the best of my knowledge, like all the proofs that have been derived to derive the concentration of the exact posterior distribution do not really rely on PAC-Bayes. And it also means that it is quite difficult to extend these proofs like to the variational approximations because we don't have such PAC-Bayes tools. And there is a question now. So, okay, we cannot prove the concentration of the regular posterior based on PAC-Bayes, but we can still do that based on other tools than PAC-Bayes, like the old school mentioned by David. But the question is, how can we do to extend these results? Because we don't have PAC-Bayes tools here. And actually, the result is that, pretty interestingly, so Ziji, so here it's Zhang and Chaogao, actually succeeded in extending the proof from the exact regular posterior base posterior to the approximation, but not using the PAC-Bayes like the variational representation of the posterior, but using the approximate base perspective. As I told you, like VI originally is defined as approximate base, but it can be reinterpreted as variational stuff, PAC-Bayes stuff, okay? And Song and Gao did not really use PAC-Bayes here. They use some kind of PAC-Bayes tools, but really they use the approximate base perspective to show this, which is actually remarkable. So keep in mind that, so that's quite of contradictory to what I've said previously, like, okay, PAC-Bayes is great for proving variational approximations and so. Actually, you can prove things without following this route at all, okay? So just like with slight PAC-Bayes arguments, but just a little of them, okay? And so this is, I think, my last slide, or penultimate one, maybe, yeah, my last slide, sorry. So just want to say two things, which is that basically, if you want to generalize variational inference, basically there are two perspectives on VI. The first one is the approximate base perspective here. And the second one is the variational perspective. I don't know whether it's interesting to say variational perspective, but like the one based on optimization and PAC-Bayes related to PAC-Bayes. So you could extend VI in two directions. The first one is, okay, using what is generally called like generalized VI. I don't know why this perspective is generalized VI and not the other, but well, the extension just simply consists in replacing the KL here by any divergence. And the second one is consisting in replacing adopting the approximate base perspective and replacing the KL by any other discrepancy D. Okay. So actually, if you choose the KL here, this is equivalent to choosing the KL here. But if you change the KL here, it will not be equivalent anymore to anything there, right? So you don't have this dual interpretation. So really, you have two different directions. And basically, if you want to study the concentration of such tools, so either being like minimized over the whole space of distributions, like not Gibbs posteriors, but other posteriors, or the variational approximations, that there is typically a need to develop PAC-Bayes bounds that will make it possible to derive such kind of guarantees. Two typical works that are relevant for that are one by AG's Pierre Alquier and G. Benjamin Gage, who derived such a concentration for forward divergences in a work published at Machine Learning in 2018. And another work by Pierre, which was published at ICML a few years later, which is not really based on PAC-Bayes. It's based on regret bounds, but like still interesting. I'm just thinking of typically, I think that last 2 weeks ago, like Benjamin presented a work on Wasserstein divergences. So this is very interesting, but still there is a lack of work that make it possible to just like relate empirical bounds, theoretical bounds, and theoretical guarantees, concentration guarantees that we can have. And I think that there was like a very interesting discussion between Pierre and Benjamin during the talk about how we can connect things. And the second part is that if people want to like extend VI in the discrepancy direction, then the work of Zhang and Xiaogao, it could be very, very relevant to do so. There's perspective, which is typically non-PAC-Bayesian, but still very interesting to connect things, and all the pieces should be of great interest to investigate such questions. And there are many other questions that can be just like raised, like typically we extend like things by replacing the KL by something else, but we could also decide to replace like the empirical loss by something else. And I mean, there are a lot of discussions that can be done. And there is, sorry, a few, just I listed a few questions that could be raised. Just the first one, I think it's quite important. The first point, everything I told you here is to say, okay, the Gibbs is an exact minimization scheme. If we relax it, you can address the variational also. It means in some sense that the rate of the variational approximation is always worse in some sense than the exact one. This is not true, okay? And if you take a look at the paper of Zhang and Xiaogao, they show explicitly how VI can provide some kind of regularization and even improve sometimes the rate of convergence of the exact posterior. So these are kind of pathological cases, but still it exists. And the PAC-Bayes route in some sense hides this. So there should be a way to improve things, okay? But still, to the best of my knowledge, there exists no very general way to present things like, okay, we have a very generic theory, a very general theory, which does not hide some stuff like that, just like hiding the fact that we couldn't improve like rates by using VI also. So I think I spoke a lot, and I'll let you conclude, like Jan. Thank you.
Thank you so much, Badr. That was a brilliant talk. Do we have questions from the audience? If so, feel free to. Yes, Zhenglan?
Thank you for the great talk. I think I have two questions. So one of them is about the so first of all, I know very little about the field, so my questions might sound a bit stupid, but I wanted to ask about the prior mass condition. Like right before when we were still talking about the Gibbs measure, the prior mass condition was something like they are basically of the polynomial order concentrated around the true the global minimizing parameter. So like, because we get to we get to choose pi only before doing all the trainings and stuff. So like, how do you guarantee such a thing like the prior mass condition when you don't know what the actual minimizing parameter theta star is? And then
you cannot really guarantee it. I mean, if your goal in practice is to just like to learn a prior distribution or so, it's not something that you can guarantee. It just like it's in some sense it's just a theoretical requirement in order to achieve a given rate of convergence. So basically, so the generic definition. So Pierre, I don't remember if Pierre gave the definition of the prior mass condition, but the general definition of prior mass conditions is more general than this one. You said it's a polynomial requirement. You are definitely right. In fact, in general, the rate of convergence is explicitly mentioned in the prior mass condition. And so typically here I'm saying your priors should be of at least polynomial order. In fact, we do in the most general setting, we do not say it should be of polynomial order. We say it should be of some order that defines the rates of convergence, okay? So deriving it is like a case by case. I mean, you need to have a model and to derive your rate depending on your model. But I just wanted to highlight that you're right saying it's polynomial. It's the one that I used, but it's not, I mean, for instance, in non-parametric setting, you will not have any polynomial order like that with something that's more just like not more complicated, but it depends on your typical model. So there are, I think, two aspects in my answer. Like the first one is that the polynomial order is very specific to what I said. So you're right, okay, but it's not always the case. You can have like relaxations of that, like a more general definition, which is not explicitly polynomial. I think that David gave a one that is not explicitly polynomial. And the second question, I mean, the second part of the answer is that I think it's difficult. I don't even think it's possible to say, okay, before choosing a prior, knowing whether it will satisfy it or not. I mean, you really, it's a case by case point in some sense. You give me a prior, I can check whether it satisfies the condition or not, you know, but it's
So
more.
doesn't that separate us from like using this bound in the actual training setting where, you know, like we don't know where the actual theta star is, and then we don't know what the prior mass condition should be, right? Because yeah, I'm still not understanding, like, if we cannot enforce this prior mass condition before all the training stuff, then how can this bound be useful?
Well, I mean, in some sense, it depends on what you're expecting. If your goal is just to say, okay, I have some truth that I do not know. If I have some truth that I do not know, will I have concentration to the truth? Then implicitly, I can guarantee you to have this concentration to the truth, provided this condition is satisfied. It's not a question of enforcing the condition to be satisfied or not. I mean, there is no really training any objective to get this satisfied or not. Just like a prior in all these works, the prior is like data free. So in some sense, it's something that I am given. Okay, I can just like, this is just a condition I can check or not. Okay, and I mean, even the condition depends on the value of the true parameter. Okay, so I think that if your goal is to learn something, to learn a prior, the question is a bit different. Like the perspective is a bit different.
I see. Okay, thanks. So the second question was that the entire thing about like this generalized base posterior, and then we're talking about the rate at which it converges to the true the optimizing parameter theta star, right? So it seems very different from the traditional Bayes, right? So in the traditional Bayes, we still have like even at points that are not the optimal, we still have valid interpretations about those. Like those are basically the prior times the likelihood. But here it seems like we only care about whether or not it converges to the basically the maximum likelihood point. Right.
It's not exactly the maximum likelihood. Like it would be like the at least the theoretical likelihood in some sense.
Yeah.
The expected likelihood point. Yeah. Okay.
Yeah. So I don't know. It seems a bit weird that we're throwing away like the extra information that like Bayes statistic could have provided us, while only focusing on the limiting behavior or like how the limiting convergence rate to that one point.
Just to be sure I understand, like, do you say you're not completely comfortable with the idea of using like large samples just to evaluate the quality of your posterior? Is it like what you're saying?
Yeah. So at least like with finite samples, we can't. I don't know. I'm making myself confused, but it seems like with finite samples, we don't get like very reasonable guarantees. If that's
I mean, so I'm not sure whether we're on the same page or not. I definitely agree on the fact that there are many different ways of assessing the quality of something, of the posterior. Definitely, I think that a lot of people are more interested in the reliability of the posterior itself rather than large sample properties or so. There are even people that are not interested at all on any frequencies guarantee. I would say that in some sense, what I did is that I defined a criterion to evaluate the quality of the posterior, which is very subjective. I agree, I admit. And I try to understand how, just like my different tools, like posterior, the Gibbs posterior, the the approximation just like behave with respect to this criterion. I don't know whether your concern was about the relevance of the criterion that I used. I think I can discuss
maybe
that.
a tiny bit about that.
I think it's a point we can discuss. I mean, it's more, I
Mhm.
wouldn't say a philosophical question, but it's just like a subjective question at least. And I mean, I think it's an interesting question. And even like in David's talk, he gave like at least two large sample properties. The first one was like the question of frequentist concentration. The second one was of frequentist uncertainty quantification. I did not address at all the question of uncertainty quantification, which is of major interest in the literature. So,
Mhm.
I mean, I think it's a subjective question in some sense, and I mean, very, very interesting, but just like just to be understood with respect to what I defined as my main interest.
Okay. All right. Thank you so much for the talk.
Thank you again.
Thank you so much, Badr. I think in the interest of time, other questions should maybe be sent to Badr directly. But with that, we've now completed the PAC-Bayes chapter. So thank you again so much to everybody who came, and again to Badr and all our other speakers. And we look forward to seeing you all again very soon. Okay.